All right, so before we get started on today's lecture, all right, so before we get started on our today's lecture, let's just do a quick review in what we already discussed, which is the first set of reaction in this entire quarter. That's the electrophilic addition of alkene, right? So in our last lecture, we went over two sets of reactions. One is halogenation, so that's this one. So when we say halogenation, we're saying that HX group or the hydrogen in that HX group is acting as our electrophile. Or alternatively, we have acid catalyzed hydration, where your H3O plus is acting as our electrophile. Right, so that's a general reaction of electrophilic addition. Now we also went over several things regarding the electrophilic addition. One, what's the nature of electrophilic addition? Now we're talking about the double bond, the pi electron in alkene is acting as a nucleophile, attacking the electrophile. It's like relatively electron rich and electron deficient. The result of this first addition is, well, two different possibilities, right? So your E plus can add to two different positions of your sp2 carbon. So we'll generate like a E here, where the carbocation will locate on the other bond. Right? So we're pushing the electron. So we're pushing the electron. We're having the pi electron forming the carbon forming a new bond with the electrophile. So you can either form this carbocation, or you can think about forming this carbocation. Now I did not draw out all the hydrogens, but when you're not so familiar with it, please draw out all the hydrogens. Now observing these two carbocation, the top one is a secondary carbocation, or we see two, and why it's called secondary, right? We're focusing on the carbon with the carbocation with a positive charge. We have two R group attached to it, only one hydrogen, and hence that's a secondary carbocation. Alternatively, if the electrophile goes onto the internal carbon, will generate what we call a primary carbocation. Right, so it's primary because around that carbon center, where the positive charge is, you only have one R group attached to it, hence it's primary. Among these two, my secondary carbocation is more stable. All right. In addition, we also went over something called 1,2 rearrangement or carbocation rearrangement. What does that mean? It's you can have shifts of groups so that you're forming a more stable carbocation. I'm going to leave it here, the carbocation rearrangement for the practice problem here. But for this one, upon forming the more stable carbocation, you can have a nucleophile, another nucleophile coming in. Now that nucleophile can be your Cl minus if we're looking at a hydrohalogenation reaction, or a molecule of water, right? So the lone pair on your water molecule can act as your nucleophile in the second step. All right, so that's in our acid catalyzed hydration. And this nucleophile, now it's electron rich, will attack that carbocation in forming our products. Whether it's like, well, I'm just going to put nucleophile there depending on the reaction. All right. So when we're talking about the name of the regioselectivity, or in this case, when we're talking about regioselectivity, we have the Markov-Jacob rule. selectivity. But at the end of the day, like if Markov Nikodym selectivity works for you, use it. We still use that terminology. But at the end of the day, what determines the regional selectivity is the stability of your carbocation. All right, so this is a quick review in all things we discussed in our previous lecture. And let's do one comprehensive problem together and see what's my expectation to you, like what a typical exam question would look like. Like this will be one of your typical comprehensive exam question with multiple parts. Right? So think about it. What are the knowledge we're using here? The question gives you the reactant, which is an alkene of water. You have H+. So by looking at your reactant and reaction condition, we can conclude, okay, so this is a acid catalyzed hydration reaction. Right. And the question asks you to first write the IUPAC name of the reactant. Obviously not the water part, but the alkene part. So write the IUPAC name, that's a nomenclature. Secondly, predict the major product of the reaction. So this one, we're expecting you to know how to predict the regional selectivity based on the nature of the reaction. And also propose a mechanism and identify the rate limiting step. All right, so let's work on this together. First thing first, what's the IUPAC name of the reactant? Well, in the IUPAC nomenclature, remember we want to put our alkene as early as possible. So we have 1, 2, 3, 4. So the name of my reactant will be 3,3-dimethyl 1-butene. All right? Or alternatively, we could say your 3,3-dimethyl 1-butene react with water under acidic condition. Tell me what's the predicted product. So we can ask this question in different ways. Now, the next question, predict the major product of the reaction. So this is one of those questions, like it may appear early in your question, but don't jump too fast in predicting the product because it's easy to get it wrong. Like alternatively, my suggestion is you write out the mechanism first and then think about what's the major product. So if we look at this reaction here, let's just say we write out what we have. It's acid catalyzed hydration. So first step, we are forming the electrophilic addition, right, to form the more stable carbocation intermediate. And that's our reaction A. Now in this process, we want to form the secondary carbocation instead of the primary carbocation because the secondary is more stable comparing to my primary. And the hydrogen will add onto the terminal position. In our previous discussion, we also already mentioned that my formation of carbocation is rate limiting. So this is going to be our rate limiting transition state, which is the formation of the carbocation intermediate. Now, do we stop here? This is the point that you want to double think before you add the water onto attacking that carbocation position. Right? Remember, for the carbocation, you can potentially have a 1-2 shift to form a more stable carbocation. Now, in this case, we have CH3 group right next to the carbocation that can undergo a 1-2 shift. Or carbocation rearrangement. Or you can also call it alkyl shift, 1-2 alkyl shift. Right, right? So for this kind of carbocation rearrangement, the take-home message here is whenever you're forming a carbocation, think about it. Can I move its neighboring CH or methyl or ethyl group or alkyl group to the carbocation position to form a more stable carbocation, which in this case we can. And we end up generating a tertiary carbocation after moving my CH3 and my hydrogen here. Yes?
Is the 1,2 shift only for methyl groups?
Well, methyl 1,2 shift works for hydrogen and alkyl groups. Now the shift of hydrogen is faster than a alkyl shift, but both hydrogen and alkyl group can undergo 1,2 shift carbocation rearrangement.
So if you had a hydrogen and a methyl both next to it, which one would you?
Hydrogen will shift before the alkyl group shift. All right. And then from here, we're ready to undergo the subsequent reaction, which is now we have, well, another water come in. To form the oxenium iron. And then deprotonate to form my final product. All right. And what is our product? Well, so this is gonna be our product. We can also ask you to write the IUPAC name of your final product. If we do that, that's, well, 1, 2, 3, 4. So that's, oh, actually I want my oxygen, my alcohol to be at a higher position. So 1, 2, 3, 4. So that's gonna be your 2,3-dimethyl 2-butanol. So if we ask you to write it. All right, so this is just a quick demonstration in a mechanism style problem in like when you're writing how to write the reaction mechanism, what are the considerations, what are the key things we care about the reaction mechanism, aka what's the rate limiting transition state, how does the selectivity is controlled via this reaction mechanism, and how to predict the reaction outcome. Yes. The formation of the carbocation is a rate limiting step for the electrophilic addition reaction.
What if you have a reaction with like a carbon ion?
Okay, so do not think about things that we did not discuss. All right, so this is the electrophilic addition reaction. Every reaction will have a different reaction mechanism. Now, what we can say is for the electrophilic addition reaction, the formation of the carbocation is the rate limiting step. Doing good so far? So this is going to be a quick review in what we discussed before. And again, in this process, we're using everything we discussed at the first half of our quarter. Yes?
Could you write out the final products IUPAC name?
Well, I'll try. I'm not very good at it. So it's going to be 2,3-dimethyl 2-butanol. All right. And again, we might also ask you the question like why we're calling this an acid catalyzed reaction, right? So we start from a H plus as an initial point, and we end up regenerate that H plus. So for this reaction, we're not consuming that H plus. It's a catalyst. Yes.
I may have just not caught it, but where does the H from like the second step go? That's on the left. Where does that go?
Which one you were talking about?
On the step before.
This one?
The H on the branch, the top branch.
This one?
No, the other H.
This one? Oh, no, I just didn't draw it. I mean, you don't have to draw all the hydrogens, that's all. I mean,
Okay.
There are so many hydrogens there, but you don't have to draw it. That's why the final product is just like that. I draw it out just to demonstrate like, hey, this is a Markov-Nikov selectivity. Your proton go to your carbon with more hydrogens on it.
Okay, but that doesn't lose points or anything if you don't draw the.
You don't have to draw it. Yeah. I mean, to be honest, I don't draw it when I draw the mechanism, but it's a very nice practice when you're not familiar with the mechanism. All right. Yes.
I have a question about when you're forming the H3O.
Okay, let me do this. So this is A, B, C. Molecule 1, 2, 3, 4, 5. Which one you're talking about?
I'm talking about one when you're forming the H3O plus, because I know there's water in H plus. I'm saying H plus has in one, like when you label one. Yeah, I'm saying how do you get that without like electron pushing? Because I'm wondering like where the electron is.
Well, so this one, if you really want to do the electron pushing, you want to draw out the oxygen ion. So the actual pushing is the double bonds attacking the hydrogen and they breaking the OH bond. And we're regenerating a H2O in the second structure.
Oh, so you're not like adding an H plus to H2O to make H3O plus, you're starting with H2O?
Well, keep in mind, like when we're having acid, your H2O and H3O plus is in equilibrium with each other, right? So the actual concentration or the position of that equilibrium depends on the pH of your reaction mixture. So in reality, in a homogeneous solution, you always have water and H3O plus homogeneously distributed in that solution. So you do not need to draw out every single like H3O plus and H2O equilibrium along every step. Yes?
Wait, so the vast majority of the time, the first step is the rate limiting step?
No, it's very specific. The position, the identity of the rate limiting step is very reaction specific. We're saying for electrophilic addition reaction, the formation of the carbocation is the rate limiting transition state. Yes.
The water that acts as a nucleophile, can it act as a nucleophile or an electrophile?
So, okay. The question here, again, like don't get yourself confused. When we're talking about nucleophile and electrophile, we're talking about every single step. What is my electrophile? What is my nucleophile? So if we zoom out to every single step, what do we have? In the first step, we have a pair of alkene and H3O plus. Between these pair, my alkene is the nucleophile, my H3O plus is the electrophile. Alternatively, in the second step, ignore the 1-2 shift in this one, now I have a carbocation and a H2O. Now in this pair, my carbocation now becomes my electrophile and my water is my nucleophile. Now it's not a real good comparison when you say if my water or H3O, like is my water a nucleophile or electrophile? It depends on what's the actual step we're talking about.
So is it kind of like the acid base where you identify the acid base first and then you assign water to the other one?
No, this is not an acid-base reaction. Or I guess it is a nucleophilic addition in the second step. Okay, let's move on to a different kind or a different class of reaction with alkenes. So that second class we're talking about is called addition reaction. So in this class, remember, when the water approaches the carbocation center, it doesn't know which phase it is approaching, right? So this reaction is not stereo specific. But our next class of the reaction will be stereo specific. And let's see how that works out. So the next class of reaction is called addition reaction or halogenation reaction. So in this case, it's halogenation. So in comparison to hydrohalogenation, the general reaction here is we're having a carbon-carbon double bond and a Br2 or your X2. It can be Br2, Cl2. And we're overall generating a carbon-carbon group. And you're adding both Br onto your carbon group, onto your carbon center. All right, so that's the overall reaction. And let's think about how this reaction is taking place. Again, several things we want to talk about, right? So first thing, what's the rate limiting step? What's the radial selectivity? And what is your stereo selectivity? So 3 goals for this reaction. Now, what do we have? Likewise, like what we did before, in the halogenation reaction, the first step is the addition. So my double bond is attacking the bromine and breaking the bromine-bromine bond. And the result of this one is the formation of an interesting intermediate. It's still a carbocation, but now it's a bridged head carbocation. All right, so what does that look like? So we have carbon, carbon with different groups around it. And I'm forming a bromine, new carbon-bromine bond on one of the carbon, and the other carbon was left with a positive charge, like a carbocation. But in this case, because bromine itself has like lots of electrons, we can easily draw resonance structures of this intermediate. So what does that look like? Well, you can think about my bromine as forming a bond on the other carbocation. Or alternatively, you could have a positive charge on your bromine. All right, so when drawing the resonance structures, again, keep in mind, when we're putting them as resonance structures, what effectively we're saying is that these structures coexist. The reality of this positively charged intermediate is an overlay of all 3 structures, right? So the resonance structure, they do not oscillate from each other. Or if you think about the reality, what we have is like carbon-carbon single bond, and you have like sort of partial bonds between the bromine onto both carbon, and that positive charge is sort of delocalized over all 3 atoms. And we have substitutions on the carbon. All right, so that's the nature of our resonance structure. And this specific intermediate is called a bridged halonium iron, or in this case, bromium iron. Right, so that bridge is saying your bromine sort of partially bound to both carbon, and that positive charge is delocalized over this entire triangle. And the other practice that we did, remember when we were talking about resonance structures, you have major contributors and minor contributors. So if we observe these structures, assuming my substitution on the carbon are the same, right? So now, assuming my substitution on the carbon are the same, among these 3 contributors, which is my minor contributor? My bromine is more electron negative than carbon, right? So if these substitutions are the same, my bromine is more electron negative than carbon, then this will be my less contributor or minor contributor. All right. What else? Well, in addition, if these substitutions are different, now imagine we can have like say a methyl hydrogen methyl. Right, so one of these carbocation will then become even more major. So comparing these two, if I have two methyl group on one of the carbon, and then one methyl, one hydrogen on the other, and then this one will become the more major contributor of the resonance. Like the reality is still an overlay of all three, but the relative distribution of that carbon positive charge could tilt towards one carbon or the other. All right. But nevertheless, what else is different? Now, the difference between the carbocation in this case, in this bridged bromonium iron, I'm not very good at this. So the bridgehead intermediate, comparing to the free carbocation we have over there, we have a clear difference. So when we have that free carbocation, keep in mind that's a planar molecule, right? So when your nucleophile approaches that free carbocation, it doesn't know which one to go. But now, in this bridged bromonium iron, when my nucleophile approaches the carbon center, the top face is being blocked because of my resonance structure, because of that bridged bromine group. So if you imagine like another like Br minus is approaching, it can only approach my carbon center from the bottom. All right, so if we're doing the arrow pushing, that must look like this, because my bromine can only approach my carbon center from the opposite face of this bridgehead bromine group. So what does that mean? It means now this reaction becomes a stereospecific reaction, or we can somehow control the stereochemistry in the second step because of this bridgehead bromine group. And our final product coming from the bromine addition reaction then becomes my carbon-carbon and my bromine will be on opposite faces. Or if we put it onto a Newman projection of looking through this carbon-carbon center bond, it means my bromine group will be anti to each other. All right. So now in this drawing right now, it doesn't look like it's stereo selective because I don't have chiral center on any of my carbon right now. But now if we put in different substitutions onto my carbon, then we'll have stereo selectivity in this reaction. Now, this anti-selectivity, I'll take more questions after finishing this part. So this anti-stereo selectivity will come to link with some of the things we discussed before. So for example, now imagine I have a cyclohexene reacting with Br2. Right, so we discussed like this reaction is going to be a stereospecific reaction to form the anti-product, meaning your bromine will be trans to each other on different faces to each other. Or when we put it here, you'll get one wedged, one dashed. Now, what's the favored conformation of this 1,2-dibromo cyclohexane? And you know how to draw the chair conformation, right? So the 1,2-dibromo trans to each other. Well, let's just do a chair. 1, 2, so one down, the other up. So that's a more stable chair conformation with both of your substitution in equatorial position. All right. Let's do this one more time into thinking about what else can be taken in. Now, this one we're talking about addition of bromine. But in this case, we're talking about my nucleophile being a Br minus. So what if we're doing the experiment in water? Now your water can also act as a nucleophile. So that's called a halohydrin reaction. So same mechanism, let's look at it together. Halohydrin, it's the same kind of reaction, just now instead of having Br adding to it, I'm just gonna put hydrogen, hydrogen, and we're saying the reaction is Br2 in present with water. What does it look like? So follow the same mechanism. So let's do this together, right? So the first step is attacking my bromine and breaking that Br-Br bond. What do we form? We form that bridgehead positively charged intermediate, which is, well, carbon, carbon, hydrogen, R group, hydrogen, hydrogen. Now this one will be here, Br, and we're dissociating a Br minus. And we have 3 different resonance structures. And also the one with carbon positive charge on the bromine. Right. And now, among these 3 resonance structures, what is my most major one? What is my most minor one? Again, the first thing we do, my bromine is more electron negative, so the positive charge on my bromine is the less favored one, so the minor contributor. And then comparing these two, we look at they're both carbon-centered positive charge. This one is primary, this one is secondary, right? So this one is the secondary, and that's my major contributor. So now with water present as our solvent, we have more water present, so my water is more likely to act as my nucleophile in attacking my carbocation from the opposite side of the bromine. All right, so what we end up getting is your carbon-carbon, bromine, oxonium cation, R group, hydrogen, hydrogen, hydrogen. Let me finish this and we'll take more questions once we finish. And then you can have another water to take that proton and to form our product, which is OH, R group, hydrogen, carbon, hydrogen, hydrogen, Br. And that's our product, right? So in this whole process, we're adding a Br and a OH onto 2 carbons of my double bond, of my alkene. Okay, I'll take questions if you have. Yeah.
Can you explain one more time why that's the minor contributor, far right resonance structure?
Okay, so among the 3 resonance structures, we first look at the position of the positive charge, right? So in this case, 2 of them are on carbon, 1 of them is on bromine. Now bromine is a more electron negative atom, and hence it doesn't like that positive charge, it wants electron. So this one is ruled out as a minor contributor. And then among the 2 carbon-centered cation, the secondary carbocation is more favored than the primary. So the leftmost is the most major contributor to the overall structure. All right. And one more thing as a side note. Now, since my overall carbocation is actually delocalized over my 2 carbon and 1 bromine, the carbocation rearrangement is no longer taking place. Like the one with the free carbocation, you can easily have 1,2 shift or carbocation rearrangement. But since my bromine atom is acting as a bridge of holding my carbocation in position, the carbocation rearrangement doesn't take place for these addition reactions. That's why I put them as 2 separate things, because it's different reaction mechanism. Okay. Any other questions? Yes?
How did you add water twice? If you added it once and then
Well, I added once to form the oxonium ion, and then these two is actually an acid-base equilibrium, if you think about it. Like whether or not this one is present or the actual alcohol is present, it depends on the pH of your solution.
So, like, if we were to be given a question like this on a test, would we need to know, like, we know?
You'll end up with a neutral form. Like, don't stop at the oxonium ion. Yeah. Yes.
So this wouldn't be stereospecific then?
Well, is this reaction stereospecific? Now, again, the stereochemistry control comes from the fact that when your nucleophile approaches the carbocation, it must approach the carbocation from the opposite face where your bromine is, right? So in this case, the bromine is already holding in position. So when the nucleophile, whether it's a bromine minus or a water, approaches the carbocation, it must approach in a different face. Or the other way to put it, my OH and the bromine must be anti to each other if we're looking at the Newman projection. Yes?
When we're given reactions where we have to come up with the resulting product, do you want us to always assume that our product is not going to have any like charges or any like, yeah?
Well, so here's the thing. If you end up here, it's probably okay. Like you'll get 95% of your grade, but normally, like, do you end up with that deprotonated form? Because this one is just an acid-base equilibrium with each other. All right. Following the same reaction mechanism, remember, like, one of the advantages of having this bridgehead intermediate is that it's no longer a free cation. So we do not have the 1,2 carbocation shift. So that can be very useful when we want to control the product and we want to make sure we do not have the 1,2 shift. So that leads us to this other reaction following the same kind of reaction intermediate. So that's called the oxymercuration reduction. So one of the questions here is, again, going back to the example we did, right? So this is the comprehensive example we just did. And we say, like, add water under acid catalyzed hydration. We're generating the carbocation rearrangement product. Right, so this one is acid catalyzed hydration, and we have 1,2 shifts taking place. This is the example we just did together. But what if I want my OH to be located on this secondary position? Like, how to achieve it? We cannot get to this product in the acid catalyzed hydration because of carbocation rearrangement. So the oxymercuration reduction is the reaction condition allowing for addition of H2O along a double bond without undergo the carbocation rearrangement. All right, so the general reaction condition will be like we have the same reactant, and the reaction condition would involve a mercury reagent water, and then a base treatment. Our product will be a OH group on the secondary position, following the Markov-Nikov regioselectivity. Well, in this case, water is the one we add onto. We end up having water added onto the double bond. The mercury and the NABH4 are my catalyst. But in this case, let's look at the reaction mechanism together in how that is taking place. And then I'll take questions if we have time. So again, the purpose here of introducing all these reactions is that we chemists, we really want to control where that reaction takes place, right? So in the acid-catalyzed reaction, acid-catalyzed hydration, my H2O is added onto the terminal position due to the carbocation rearrangement. But in this case, I want to precisely control that my H2O added on the 2 carbons of my double bond without undergo carbocation rearrangement. And that's why we're introducing new reactions again and again and again, because we want to control the reaction selectivity. So let's look at the mechanism of the oxymercuration reduction together. So making a link in what we did before, which is like, how do we prevent sigmatropic, how do we prevent the 1,2 rearrangement, which is you form that 3-membered intermediate. So in this case, it's the similar idea. The first step is the formation of our nucleophile, of our electrophile. So the actual structure of my mercury reagent looks like this. And what we're doing is, well, we're saying that it's very easy to break that mercury-oxygen bond in forming a acetate anion and a mercury cation. And this is going to be our electrophile, right? So obviously this is electrophilic. So first step. Now from here, you should be very familiar in how to write out the rest of the reaction from this nucleophile. What do we know? Well, it's the same thing. We start from my carbon-carbon double bond with like different groups on it. You have a Hg plus OAC, right? So that's our electrophile. Now, we're having the attack onto your mercury. And we got the same kind of 3-membered intermediate that we see before with bromine, which is my carbon-carbon RH positive with Hg attached to OAC. Resonance to the other carbon-centered positive charge with Hg OAC. And then, again, resonance with carbon-carbon Hg plus OAC. My drawing is a little bit ugly, but you get the idea. It's the same kind of 3-membered carbon, 3-membered positively charged cationic intermediate, where the reality is, you know, this carbon-carbon and Hg sort of like binding like that, where your carbocation or the positive charge is dispersed over all 3 atoms. All right. And in here, what's next? The next question comes is, well, now we have 2 different carbon-centered cation, and depending on the relative substitution on these cation, the left one is the more major contributor. And this one is a minor contributor with the carbocation on a primary carbon. So when my H2O comes to attack my carbocation, that goes from the opposite face from where my mercury is. And we generate my third step, which is my carbon, R group, hydrogen, your OH3. And then on the other carbon, we have hydrogen, and your mercury. Or deprotonate this one through an acid-base reaction. And then the last step is the reduction of the HgOAc, which magnesium I don't expect you to know. And the result will be your hydrogen forms at the anti position comparing to your OH group. All right, so for this reaction, let's pause here and think about what do we have, writing out the reaction mechanism. First thing, my hydrogen still adds onto the carbon with more hydrogen at the end. So we have Markov-Nikov regio selectivity. Your OH and the hydrogen will always be anti to each other. Note that I'm not specifying the actual absolute stereo configuration. I'm just saying the new OH and the hydrogen added to each other, they must be anti to each other. Now, whether or not we have R or S, that's out of our control. And for this reaction, like knowing how to predict the selectivity, knowing how to predict the regio selectivity and stereo selectivity, and know why do we use it, right? So the reason we use it is we want to obtain the Markov-Nikov regio selectivity without undergo the carbocation rearrangement reaction. Okay. Any questions before we finish? Yes. For this reaction, we're nearly always going to use this mercury reagent, which is the mercury acetate. Now, in reality, organic chemists nowadays don't really use it because it's toxic, but on paper, we are still using it because it's a nice introduction to the oxymercuration reaction. Yes?
So the next option you said, can you use that one time about like we do this because we don't want to do carbon?
Okay, so here's the thing. Now, imagine you're a process chemist at a big pharmaceutical company. Your boss wants you to synthesize this molecule, and you only have these two starting materials. Now, an acid catalyzed hydration will get you the wrong product, right? So the purpose here for organic chemistry is I want to teach you as many tools as possible so you can construct the new chemical bond in a controlled fashion. You want to know what to come out from your reaction, right? You don't want to just throw in random things and imagine like a miracle will happen. All right, so in our next lecture, we'll talk about hydroboration oxidation, which is the one we'll get anti-Markov-Nikov regio selectivity. So stay tuned, see you Friday.